Hello. Now, this one's about another servo tester project. I needed something a bit more sophisticated than the little 555 one I showed earlier. And this is one I built using a technique I've used for many years with PIC systems. It uses the built-in hardware, the output compare register and the timer to give accurate, or pretty accurate, allowing a tiny software overhead, output pulse times with it running completely in the background away from the main program because it's purely interrupt driven. Now I've done a PDF of the program and I'll link it below in the description so you can look at it on screen or print it out. But as you can see, I've also got it on screen at the side of this video showing the device, so I can describe them both together. I mean, the hardware design is next to nothing. It has a PIC, little 14-pin PIC. It's running on its internal 32 megs oscillator. It's got a decoupling capacitor plus a little ceramic underneath it, and a 10k pull-up on the reset pin. Then everything else is the servo side, basically. There's 4 pins connect to the individual servo connector pulse signals, and there's 4 inputs from these pots, which are just fed between the 0 volt and 5 volt on the end of the pot. And the result is, the way I've got this set up, the first 2 channels give the traditional 1 to 2 millisecond pulse with 1.5 in the centre, and the second 2 give an extended range 0.5 to 2.5 with 1.5 in the centre for the wider range servos. And with minor change to the program, you can make each do whichever you want to suit whatever servos you want to be able to use. Now, the knobs don't line up exactly with the centre point of the pots. They've got to be just offset slightly to be at 0, but I've got used to where they are now. The only other bit on it is that 2 of the sockets, that one and that one, are running from a higher voltage. I've actually got the little regulator set for about 6.2 volts. It directly feeds the 2nd and 4th servo connector, and there's a couple of banks of diodes in series with it to drop it down by about 1.2 volts to the PIC, and then I've got it set at the 5 volts at the PIC. It's just because these high power servos, these very high power ones, can run up to about 7 volts or so. So when I'm actually testing it as part of one of my robot projects, which you see there's a bit of a leg there, it allows me to use higher torque nearer the full power of the servo. But anyway, onto the software. Looking at the program here, a lot of now you can't use this as a literal program unless you're using the same compiler as I am, which is the CCS compiler for a PIC, which integrates with MPLAB. The first part is just the notes and definitions. You can see I've got the pinout I'm using in the header there as comments, so you can see which pins on the PIC connect to what, and that's just about all you need for a wiring diagram, as long as you put the 0 volts and 5 volts in the right places. That's bits of headers for the compiler, just saying what device it is, that the ADC is to be configured as a 10-bit, so 0 to 1023 values, the clock speed on the internal oscillator, and then the fast I/O mean that the in a directional allocation on the pins is permanently set to what I define, rather than being dynamic depending if the user's input or output later in the program. It just makes the input and output routines a lot faster. That's something I normally use. Very rarely want to dynamically change a pin between input and output unless it's for a special purpose. Then these are the actual variable definitions I'm using. Index is just a counter for the servo channels or general increment timing. Servo times is the output register, if you like, that has the count that will be used by the output compare updates. So that's in units of the timer speed. So in this example, I've got the timer running at 2 megahertz. So it's 2000 counts per millisecond. And time now is a variable that's read from the timer, just to know relative times for setting things up. Time set is an updated register that's initially used with time now, plus the value from the servo time, and then later on it's just incremented by the servo time, which I'll show you a bit further down. Shift register is just a register that I use to start with one bit in it and then left shift it through, and that's copied to the output to turn whichever output on. Now, this routine can also work with slight modifications with a hardware shift register, and if that's clocked by the output compare pin, which I'm not using an output on this, it doesn't need it, but if you had an output compare linked to a pin to set that to trigger the clock on the shift register, and at the initialization at each cycle, you set the data, use another pin to set a data input to 1 and then clear it once the routines start cycling. You can use just a couple of pins for clock and data and control, say, 8 servos, or even up to 16. There's no reason 16 still gives you a reasonable frame rate, but 8 can give you quite a fast frame rate. That leaves less pins, and because all the timing is controlled directly by hardware, it is sub-microsecond accurate, or whatever the timer clock rate is. Anyway, this is a slightly simpler version that uses purely the pin connections directly. Right, then there's lots of notes in it as well that say what it's doing and what's what. Now, I have a filter routine in here because there's always normally a little bit of jitter depending on the noise on the supply, especially when you're running motors like this. There's a little bit of jitter from the pots through the ADC, and if there's enough noise as the servo moves, it can cause its own jitter because it's upsetting the voltage and upsetting the ADC reading slightly. So I've got a filter which basically just adds the value to a register, then divides it by 2 to average it, and then keeps doing that through 8 stages. That's the filter order value. So it filters out or averages out noise very effectively without slowing down the response too much. As you can see, for manual control for testing, there is a nice smooth response, and you don't notice any lag, but also there's no jitter or jumping about. That's the actual routine at the end of the program. So that's just memory allocations for the filter storage and definitions and a prototype. Now, this is the main part of the overall routine for the output section, which you can do separately if you're feeding your own values to the servo times data. This interrupt is executed when the output compare register matches the timer value. So it's guaranteed to be, even if you don't initialize anything, as long as you've enabled interrupts, it's guaranteed to be executed at some point as the timer cycles through its range. So I'll go to the initialization part first. This is where it sets up a new cycle. So basically, when the index gets past 14, because there's a lot of dummy outputs in it which never do anything, just purely to give the overall frame delay. But this is the new cycle setup. Sets the index value to 0, sets the shift register storage to 1. That's just a 1 byte storage. It sort of sets so there's a high bit in the lowest order bit. It gets the current time from the timer in that line. Again, these are using the compiler functions. If you use a different compiler, you'd have to use something else, or get it directly from the PIC register or any other device you're using. There are similar hardware features, but obviously with different instruction names and everything in a lot of microprocessors, including Arduinos and whatever. So it gets the timer value, then it adds that to the time defined for the first servo pulse. So it's servo time 0 in that case, it's because the index is 0, and puts it in time set. Then it sets, or it copies rather, or writes the shift register to the output port. So that 1 bit then appears on the first output, bit 0 of the port. Then it sets the counter compare register to time set, which is pretty much current time plus the duration for the first servo output. Oh, I didn't notice that. I've actually got that duplicated. It outputs it again there, which will be redundant. It doesn't matter. That could be taken out because it's not needed. Anyway, then that's the end of the interrupt routine. Normally, for the rest of the cycle, because the index is lower than the limit, so it starts here, it shifts, it moves the shift register variable along 1 bit, and then immediately outputs it. So that turns off the previous bit and turns on the next bit. So at the start, from that first initialization routine, it would have turned that one on. And then at next cycle, because the bit has moved a lot, been shifted along, all the others are turned off, that's turned on. Then the next interrupt, it'll turn that one on, and so on. And it also then adds the servo time for the next servo, because it's already incremented the index, to time set. So time set is time set plus servo time index. Then it updates the capture compare, or the output compare register, with that new time. So that set it up to interrupt at whatever count ahead that, and whatever time ahead that value defines, which depends on the setting in servo times. So basically, it will keep interrupting, and then every interrupt, it sets itself up to interrupt again in a certain time. After it's done the number of channels, it's just dummy cycling, if you like. Once it's passed that num servos is the number of channels, I've got that defined somewhere a bit higher up there, number of servos 4, because that's what I'm using on here. That's all the outputs I've got enabled. Once it gets past that, it just dummy cycles with an output 0 to the shift register every time, because the shift register bit is already past the output pins, or it's completely been shifted out of that shift reg variable. So it's not really doing anything to outputs, they're all 0, but it builds up the rest of the frame time to somewhere around 20 milliseconds to give a practical repeat rate. So that is the essence of how it works. And other than initialization, that's all the program needs to do to keep the servos running. The rest of the program is the start of the main routine. So that was just the interrupt routine. It sets the inputs and output pins as appropriate using the truss registers. Configures the ADC. So that's running on its internal clock, and it tells it which pins are being used for analog rather than digital. Again, these are compiler functions that will vary with the compiler using, or you can just directly configure the registers in your microprocessor if there aren't functions to do it. So because this is working off pots, it needs analog inputs. If you're using it for something that was purely outputs from your own program, you wouldn't necessarily need the analog inputs. These are just because it's using pots for manual testing. Then it sets up the timer, which is the one that's being looked at by the output compare function. And now, again, I've got a description of what it's doing. It's 32 megs internal oscillator, and the timer source is the oscillator divided by 4 for the time base. So that's then divided by 4 again by the prescaler for the timer to give a frequency of 2 megahertz. So it's divided by 4 and 4 again. So it's divided by 16 with a 32 megs input to give 2 megahertz. So 0.5 microsecond resolution on the timer. And that configures the output compare function in the device, which you've got to have something to enable it in set it in compare mode rather than capture mode or one of the other possible modes for the hardware. But it's just a dummy function effectively there, the compare toggle, because there's no pin allocated to it. But it enables the compare system. And again, just some more notes there, references to frequencies and time and things. And then it enables the interrupts so that the capture compare or the output compare device in the chip can cause an interrupt when the compare occurs. And the main loop, you could do whatever you want in this as long as you update the servo times data to control the servos to whatever you want. In this one, as it's for manual testing, it reads the ADCs in sequence, stores the ADC value in the pot 0, 1, 2, 3 variables, and then passes those to the filter routine. That's at the bottom of the page there, or part of it's visible. That tells it what channel of the story to use in the filter routine, so that the pots don't get confused with each other, and the pot variable. Then, depending on what I'm trying to do for times, that's shifted by 1 bit or 2 bits after the result to multiply by 2 or multiply by 4. And then the offset for the minimum pulse length is added. And it's got a note there. For this, so for 1 to 2 milliseconds, the count's doubled to give 0 to 2000 range from the ADC and filtering, and then 2000 added, which once it's halved, that gives you 1 to 2 milliseconds total range. The other one has the pot value multiplied by 4, so that's 0 to 4000, and 1000 added, so you've got 1 to 5000 count range, which gives 0.5 to 2.5 milliseconds. And this is the filter routine. Now I've got the ADC limiting routine in here as well, which just clips 12 off either end, or 12 and 11 really. So the output is limited to 0 to 1000 exactly, rather than 0 to 1023. Just to stay within the absolute limits for the servo times, because it's multiplied up. And I don't want to force the servos past the end stop, as long as you plug them in the right output, of course. And this is the actual filter stage, which you can see the first one there is pretty obvious how it works. It adds the new input value into a variable, and then right shifts the variable by 1 bit, which divides it by 2. So it's just an average routine. It's the old plus the new, and then divide by 2. The loop does the same thing, but through consecutive storage registers in the array, still called consecutive variables in the array. So it's actually averaged with the previous result 8 times, which gives a lot of jitter removal, but no noticeable in human terms, if you like, for testing delay. It's still very responsive when you turn the pots. So that's the overall routine. And it returns the 8th bit, because it's got filter order 8 stages. It returns the 8th variable out of the array. I mean, the pointer there is just to save some arithmetic having 2 dimensions in the array everywhere. When it's doing these, it means if it's only got to have one calculation for the offset rather than 2 calculations for the offset in every one, just save at a time. But that's the overall program. I hope it's some help and some interest. And as I say, if it's not got exactly the same compiler, you can only use it as a concept. But I hope there is enough information so if you want to, you can translate it to different compilers or completely different microprocessors even. And again, anything that's got an output compare register that can work without interrupts being masked in the main program, so that's not delayed, should work equally well. I mean, I've used this again in the concept, though I rewrote it for this exact version. I've used the concept for many years, and I used to use it with some little 4 megs PICs 16C73 or whatever like that many years ago, before the F-series came out. Again, I wasn't using these digital servos back then. I don't think they existed, but for normal servos and now with high resolution stuff, the digital servos, everything seems to work very nicely. And like I say, there's no overhead, no weights or anything involved in the main program. You can do whatever you like there and get the data you're using from any source you wish. And as long as you don't block interrupts, it'll just work. Okay, anyway, thanks for watching. I hope it's interesting. Any questions, put them in the comments. And please like and subscribe if it's useful or interesting.